Thank you very much for the invitation. How does the virtual part work? Can people also ask questions in the chat? Yeah. And who's responsible for letting me know if there's the question?
Well, they can unmute and ask.
They'll shout. Okay. Okay. Someone will let me know. Okay. It's a new experience giving a talk without a mask on. I feel a little bit naked after wearing a mask for so long. So I want to talk about some joint work with Venugopalan. And maybe before I forget, let me just emphasize that there's very little that I'll talk about that's actually new. So most of this is due to other people. In most cases, I'm just talking about a new way of looking at some old result. But the general direction that I want to go in is, suppose I have a symplectic manifold which degenerates to something that we call a broken symplectic manifold. That's the X with the extra line. And then there should be, and sometimes is, a tropicalization formula, which says that if I'm doing some sort of curve count in X, then this can be written as a sum over tropical graphs gamma, with some sort of decoration, and then you should take the product over vertices in that tropical graph, and then there's some sort of curve count associated to some component of the broken symplectic manifold. So let me start off by describing what I mean by degeneration. So I'll call this tropical moment maps. So let's say that T is a torus, T is its Lie algebra, and I want to assume that the decomposition of the dual of the Lie algebra to some Dilson polytopes. Dilson means that primitive vectors at any phase form a basis for their span. And so then I let T sub P for any polytope P in this decomposition be the annihilator of the tangent space at any point in this polytope. The torus generated by those directions, and so then suppose I have X a symplectic manifold. I want to consider a continuous map with the following property. Suppose I take any C in this Lie algebra for one of these polytopes, compare the psi with C, and this should be smooth in an open neighborhood. Sine inverse of P, and it should, these together should generate TP action. And then this data with the decomposition and the psi is the tropical T action. Any questions about the notation so far?
So you have a bunch of actions in the same symplectic manifold, one corresponding to polytope in your decomposition, is that right?
Yeah, but remember that they all form one map. So it's sort of, just to give maybe a simple example. So so suppose I would have just a Riemann surface, say, And my polyhedral decomposition sort of looked like this, for example, and I could project down here. And then what I'm saying is that I only necessarily want the map that is given by projection to generate a torus action near the polytopes of higher codimension. There's no condition on the interior here, because on the interior, these TPs are just trivial. So let me give sort of a. Let's wind this up. Let me give a more complicated example. Suppose that X is the coadjoint orbit of UN, so let's identify that with Hermitian matrices. By n is eigenvalues ordered in increasing order. And so this is diffeomorphic to the variety of full flags in CN. And so one way of getting a map psi here is this technique due to Gelfand and Cetlin, which is if I have an A in X, then I can take A sub K, it's K by K minor, and upper left position. So I take the smaller matrices nested like this, and then I take lambda Kj to be the jth eigenvalue of this minor. Okay, and then I can put all of these eigenvalues together. And this gives me, well, assuming I don't include these, then it's n times minus 1. So this gives me a bunch of real numbers, and so the lemma here, which appears in various papers of Gelfand 50s, is that if I take the image of X under this map, then it's the set of tuples that satisfy these interlacing inequalities for all K. So Kj should be less than or equal to K minus 1j, and be less than or equal to Kj plus 1. Okay. And let's maybe just recall the proof of this in case people don't know it. So let's just see why the eigenvalues of, say, the n-1 by n-1 minor satisfy these inequalities. So we can assume that A is of the following form. Let's put its eigenvalues of the n-1 part, n-1, n-1 along the diagonal, zeros elsewhere. There'll be something down here which will be arranged to make the trace match up. So some of the eigenvalues has to be the the trace that's already determined by what these are. And then there'll be some numbers here, A1 up through A minus 1 and A1 bar up through A minus 1 bar. So if you take the determinant of this thing, then you get the product of these things, the product of the minus 1j's minus t, and there are two possibilities for the last thing. Well, either I just take the last diagonal entry here, or the other possibility is that I shouldn't have taken all of the diagonal entries. I should have skipped one of them and taken an AJ and AJ bar. So if I skip it, that's equivalent to putting an AJ minus 1t in the denominator. So here, this is from 1 to n minus 1. But I know on the other hand that this is equal to the product of the lambda n minus j minus t's equals 1 to n. So this gives me an expression for, well, there are two products here. There's the product of the eigenvalues of the n by n matrix minus t, and then I can put the n minus 1 j factors in the denominator, and this then is this thing on the right, aj bar divided by n minus 1 j minus t. And now you compare residues. So the point is that all of the residues here have the same sign. If there were two poles adjacent to each other without any zero in between, then the two adjacent residues would have to have opposite sign. And since the signs here of the residues are the same, this means there has to be 1, 0 each pole. And that's the same thing as saying that the interlacing inequalities have to hold. So this is taking the eigenvalues as a continuous map, but it's not smooth, because when the eigenvalues coincide, then there could be singularities. Okay. But where they are smooth, they generate a Hamiltonian torus action. So the flow of each component, say if I think of one of these eigenvalues as a function on the coadjuvant orbit, then it's generating rotation in the corresponding A. So this is an example of such a psi. And well, it's not hard to come up with a sort of polyhedral decomposition which is compatible with this. So let's choose the problem that makes it not a moment map is when the eigenvalues come together. So if I introduce some polyhedral decomposition which prevents that, then I'm okay. So choose epsilon bigger than 0, and then take the eigenvalues, say lambda p plus 1j minus lambda kj to be bigger than or less than epsilon. So something like this. These will be the polytopes of maximal dimension, but then you'll get a bunch of intersections from this as well. So that would be a good polyhedral decomposition. Say in the case n equals 3, what you're doing is you have, if I just look at the eigenvalues lambda 2, 1 and lambda 2, 2, then they have an image of square like this. And what you're doing is you're choosing a polyhedral decomposition, which sort of separates out the part that is touching the edge of the Weyl chamber with the rest of it. Any questions about this example? Okay, so then this triple X p psi is a topical action sense above. Oh, that I wasn't supposed to do. Okay. Next time I accidentally write in the one that doesn't move, please let me know. So let's talk about what sort of degenerations we're considering. So the broken symplectic manifold associated to this data is the union over all p's in this decomposition. I take psi inverse of p and I divide by TP. Okay, so in the example of a Riemann surface that I described before, what you would do is you would contract these things to points, and you would get a nodal curve with the genus one components. And so this is the union of so XP we think of as the union of all over all faces. Psi P of psi Q of TQ. So if one of my polytopes is like P1, then this XP1 would be T2 that I get by degenerating that circle. And so we'll also need some stretching data. So stretching data in this context means a collection of dual polytopes inside TP. And I won't go into the details of what this means to be dual to P, except that there should be sort of a phase inclusion reversing bijection between polytopes in the one decomposition and polytopes in the other decomposition. So here you sort of the dual to a point should be an interval, and the dual to an interval should be a point. And so if you glue this together, then you'll get some picture like this. So the dual complex is the union of all of the p duals modulo sort of the obvious identification of faces. So then there's something we call XP bar. So XP bar is like a thickening. So we take epsilon inverse, take a small multiple of the dual polytope, and we take sine inverse of Q and TQ for each of those things here. So in this example, if P is a point, epsilon P dual would be epsilon. And then when I take X P bar, what this means is whatever this hypersurface was, let's call it Z, it means I take Z times S2 and I mod out by S1. So in the sort of relative Gromov-Witten language, this would be the projectivized normal bundle, the neck piece associated to the degeneration. And then, So we also allow some Lagrangian, which is contained in cylinders of interior of some polytope. It should be true for Lagrangian with stretch in between regions as well, but we just haven't done the general case yet. And so then the theorem, which, as I said, is due to many people in similar contexts. In algebraic geometry, this is the GW theory, is that if I want to count curves in this cell, at least if I do rigid curves, then there's some next stretching limit, which is the same thing as rigid broken maps. So what's a broken map? So a broken map with graph gamma consists of two things: topical structure on gamma and so what is a tropical structure? Well, it means that for each vertex, I pick some region of the manifold that I want the corresponding curve to go in. And then I have, so this is E maps to P of E. And then I have another map from vertices into this dual complex. It's like some position. So that in the next stretching limit, this records how far out the neck it landed. Say you were, taking a neck and taking next lengths of capital T as T goes to infinity. It could be that you have a bubble developed like exactly halfway along the neck. And then this position of V would be like halfway across the corresponding interval in the dual complex. Sort of records how the neck parameters behave after rescaling. And then there's an edge map. This is some slope map. And so we call both these maps tau. And tau of E should contain the difference between the positions whenever E joins V plus to V minus. And then for each vertex, there should be a map. From some marked curve CV into X of the thickening P of E. And they should satisfy some matching condition. So the matching condition says that.
First one is the position.
Say it again.
The first map is the position.
Oh no, the first map records like which stratum of the broken manifold it lands in.
Yeah, so it's like okay.
It's just a polytope.
Yes.
Yeah. So in theory, each curve in this broken map, it could either land in here or land in the neck piece here or in here and here. 5 possibilities. So that's the first thing that I want to record. And then if it lands in here, then this tau of V is saying like, how did the position of that bubble relate to the neck length parameter in the rescale limit.
Okay.
So it could be all the way close to this thing or all the way over here and so on. And these tau of these, they basically record how the curves, the multiplicities of the boundary divisors, how they're going in here. So the matching condition says that in some local coordinate near the nodes, that the limit of z to the minus tau e on one side, the minus should be tau z to the tau of e plus of z on the other side in cylindrical coordinates. So this is what's in Eleni Iannel's paper. She calls matching of derivatives. In the multi-directional SFT case, if it's hitting a corner, then you have the ratio of derivatives on one side has to be the ratio of derivatives on the other side. This is the same condition. So let me give an example of how you might use this to compute a disk potential. Let's go back to the example of the flag variety. And let's take L monotone torus. So let's assume that X has its monotone symplectic class. And that was the monotone torus given by psi inverse of mu. Mu is the in the center of psi of X. So if you make a good choice, it's actually monotone. And so then associated to a Lagrangian like this, you have a W, which maps on from I1 of L to S1 to C, let's say. So that it's a count of Maslov index 2 disks. And so the point is that for the polytope we chose, and for epsilon small, L degenerates to a toric piece. And so in toric varieties, we have the Blaschke classification. Blaschke products. And so we know what the disks inside XP0 are. And now the point is that you can just check that the only Maslov index 2 disks are minimal area disks. Zero area. Have tropical graph trivial. So it is possible to have broken maps which go on into these other components of the degeneration, but just because you know exactly what all of the areas are, they can't contribute to this Maslow 2 disk potential. In my picture that I had before, so in the n equals 3 case, remember we're cutting like this, and we're putting the torus as the fiber over this point, and the Maslow index 2 disks that we're interested in sort of go like this. But I mean, there are disks that go here, but the area of these is something like at least 2 minus epsilon or something. It can't be as small as these disks. So then you get this formula for the potential, which is in getting the spelling right. W of y is the sum over all possible j and k's. I have a y to the epsilon k minus 1j, epsilon kj, plus y to the epsilon kj minus epsilon to the k minus 1j plus 1. So anyway, that's now the way that they did this was by looking at what's called toric degeneration with a small resolution. So the only point I'm making here is that if you have these sort of SFT methods, you don't need to do it that way. Well, this is sort of in the direction of the formula that I first wrote in the summary part of the talk. But the issue here is that the moduli spaces that you get in degeneration, they're not products, right? They're fiber products because of these matching conditions. So, so the goal now is to sort of split the matching conditions to get something which is really a contribution, a product of contributions from each piece. So let's suppose that XP is now toric for co-dimension P bigger than or equal to 1. This assumption shouldn't be necessary, right? Like if I look at Bourgeois' version of SFT, there's nothing that says that Z mod S1 has to be a toric manifold. You just take a Morse function on Z mod S1, and then you have in between the levels of your buildings, that you then have these broken Morse trajectories. So that would be a special case where the tropicalization works. But in this multi-directional SFT, we don't know how that's supposed to work in general. So I'm going to assume this is toric, and then I'm going to take a Lie algebra vector T, and so then I'm going to replace the matching condition by saying that instead of the matching condition holding on both sides as an equality, I want to put a t to the nu in here, t to the nu here. So the thing that was there before was something like this, minus of z, to the plus p of e, plus of z. Okay, and there are going to be now opposite signs for the t. So I'm sort of, instead of saying that they're equal on both sides, I'm saying they're equal up to the action of t. And now take the limit. Take the limit as t goes to 0. This, or infinity. This would be like in the Morse case, saying I take Morse trajectories in between the levels and make their length bigger and bigger and bigger. Eventually, I'll have to get some breaking. And so the result of this are something we called split maps. Well, there's some bubbling that could happen in the limit. So they have new combinatorial types. And twiddle satisfying some the quantum generalization of the Kohn condition in Fulton-Sternfeld. So Fulton-Sternfeld looked at a sort of classical problem of if you have a diagonal in a toric variety and you want to take its Kunith decomposition, what's an explicit formula for that Kunith decomposition? So they say it's a sum of product of T orbits, and there's an explicit Kohn condition there, some combinatorial thing, and there's some more complicated in this situation as well. So I'm not going to actually describe in detail this Kohn condition. Instead, I just want to give some more examples of how this actually works. So one example is take X to be the cubic surface, a cubic surface in P3. So for example, you could take the Fermat cubic which is defined by the equation x cubed plus y cubed plus c cubed w cubed equals 0. And it's a result of Cayley and Solomon from 1849 that in any cubic surface there are 27 lines. So what is a line here? So this is a holomorphic curve that when you take its image in P3 is just a P1. You can write these down explicitly in the case of the Fermat cubic. The lines look like say x CBZ or some roots of minus cube roots of -1. So a cubed and b cubed should both be -1. Explicitly check that. So the way Mumford proves this thing, this textbook, he just says degenerate any or deform any cubic to the Fermat cubic and check that this number is invariant under deformation. And then you get 9 lines from these A's and B's, but then there are a couple other choices of where you can put the A's and the B's. Those give you the other 18. Okay, but from the sort of more recent perspective, this is some Gromov-Witten invariant for some minimal degree. We're looking for the one way to say it is you're looking for the curves whose Chern number is 1. So how does this go from the SFT picture? Well, X is equivalent under deformation to the, well, first of all, it's a result of Flesch. This is a 6-time below. P2 at generic points, but then since everything we're doing is invariant under deformation, you might as well take the 6-time Tauric law. So this is the toric variety whose polytope looks like this. The way I'm going to draw it is not obviously the blow up, but it's traditional to sort of draw there are a bunch of -1 curves and a bunch of -2 curves. And I'm going to draw the -1 curves as the long edges. And then the -2 curves, short ones. So, avoid with my talk, you can check that this is a 6-fold blow up of P2. And then the decomposition that we'll take is just, the problem is caused by the, in the counting the Gromov-Witten invariant is the -2 curves, because curves with self-intersection -2 can't be regular. But, if I use SFT, then, I can cut each -2 curve into a 2 -1 curves. Like this. And so then I can just write down what the split maps are in this case. So there's going to be a matching condition at each of these boundaries here, but I can degenerate this matching condition to either, it's the diagonal matching condition in a P1, which I can degenerate to either point times P1 or P1 times a point. So it means I only have a constraint on one side. And then these will be regular, and you can just write them down. So like one example of one of these curves is just this purple inverse image of this purple face. And then I can sort of extend that to arbitrarily many times on either side using the -2 curves. Let's see, I should have one more here. Which one am I missing? I can do, how many more should I have? Should have 9. There are 3 choices of how much to extend on either side. So I also have, say this one and this one, this one and this one. And I think I left off a couple more. See, 1, 2, 3, 4, 5, 6, 7, 8. I'm missing one. Which one am I missing?
All the way from both sides.
Two extensions on either side. Yeah, maybe that's it. Okay, so the last one will be I have the -2 curve, the -2 curve, the -1 curve, the -2 curve, and the -2 curve. That still has Chern number 1, right? Because adding these -2 curves doesn't change the first Chern class. And so what are the corresponding tropical graphs? Well, the dual complex in this case is there are 4 vertices along each edge, and there's this polytope in the middle that looks like this. So some of the tropical graphs that correspond to these purple things is I can just say have 1 vertex here, or I can have a tropical graph with 2 vertices, or 3 vertices like this, etc. And so those 27 tropical graphs correspond to the 27 lines. Okay, we can also now do the same thing for disks. So disks in the cubic surface. So it was conjectured in Sheridan that the number is 21. And then the proof subsequently appeared in Well, I first saw the proof in Pascal and Tonkinov, but maybe it's also in Nishinu et al. And Fukaya. It appears in different places, but so here you're taking just the Lagrangian that's in the middle here, and you're playing the same game. So now my dual complex is the same thing. This thing with 4 vertices on either side, on all sides, and but now I'm looking not at curves in the boundary, but I'm looking at curves that start in the interior. So because the Lagrangian is in the middle piece, there always has to be at least one vertex starting here. But now I can do the say go to the boundary in several different ways. So, for example, I have just the Blaschke classification gives me these 3 disks. So those would be disks that go to the boundary like this. So I have a tropical graph which goes like this, or one that goes like this, or one that goes like this. And once I get to the boundary, then I can again start adding on these -2 curves. So adding on this -2 curve would move in this direction. So then there are, hold on. I have to go to one of these facets first and then add on. Okay, so there's one that looks like going straight up here and then adding on a -2 curve that's adjacent. I won't write all the tropical graphs down, but there are 21 tropical graphs here, which contribute to the potential. And so the potential that you get in this case is cube of y1 plus y2 plus y3 minus 6y1 y2 y3 modulo the relation. The pi1 has 2 generators, not 3. So relation y1 y2 y3 equals 1. Okay, and there's a more general result now. Sort of recent preprint of Mark's students, McLean students. But I just wanted to show you how to get this by SFP. Let me just finish by saying what our motivation for this was. Any questions about the examples before I keep going? Yeah.
So can you compute the potential for the multi-space of civil vector bundles over real surfaces using this kind of method?
I haven't, no. Which isn't to say I just haven't tried that much. Maybe it's hard, maybe it's easy, I have no idea. Yeah, so that's another example where you have this sort of map psi. In that map case, the map psi is given by the traces of the holonomies. You take a Riemann surface and then you take circles which give you a Pants decomposition. And then there's a recent preprint of Galkin, and I forget the name of the collaborator. Someone from India, from Tata, I think, who show that the potential that you get this way does in fact give you the quantum cohomology. I think that's the result of that preprint.
I think they can do this for lower genus surfaces, but not for higher genus.
Right, yeah, that's right. Yeah, thank you. Yeah, so it would be interesting to see whether you can actually get the potential as a discount from this technique as well. Yeah. Okay, let's see. Okay, so, oh yeah, I just wanted to mention one other thing. There's a, about this tropicalization formula for spheres. from the algebraic geometry point of view. This appears in a recent thesis of Lee, who's a student of Bernd Saber. So, it's again, under this assumption that the XPs are toric. So I just want to close by saying what our motivation was. So in general, these tropical formulas are likely to be very complicated, but there's some theoretical consequences of just the existence of this kind of formula. So the motivating question for us was, when is Floer theory, Lagrangian Floer theory defined? So if I have a Lagrangian inside X, then I have this space of so-called projective Cartan solutions. So I take all odd B's so that D is the default insertion. If I sum these over D, I should get something in the span of the identity. Whatever that multiple is called W. And so taking the W gives me another definition of the disk potential. And the Floer cohomology HF of L, I would think of it as some sort of space that fibers over the MC L. So for each Mori-Cartan solution, you have a twisted differential, and this is a invariant of L. But if your MCL is empty, then you're sort of out of luck. Well, you could say the empty set is still an invariant, but it's not a very interesting one. So, so one application of this is to say that suppose that L is contained in inverse image of one of these P's, and X sub P is toric, and also L. So locally, it just looks like the toric picture, and then you get that MCL is not empty. And the reason for this is that in this sort of completely degenerated limit, you get a torus action back. You've split the matching conditions. So when I act by a torus on this piece containing the L, that doesn't mess up the matching condition anymore. So the sort of standard complex structure that I take on the XP is invariant. And then once you know you can use an invariant J, then all of these MDs appearing in the projective Mori-Cartan equation go away, except for the M0, which has to be a multiple of the identity for degree reasons. So this is sort of the generalization of the result of Bukaya and collaborators, which says that MC of L is non-empty for toric L. So here you only need it to be toric locally. So I'll stop there.
Questions?
I have a question. So this multi-directional next stretching thing, can you like elaborate maybe in more like familiar SFT type language, like what exactly the curves are that you handle that setup?
Yeah, so the example would be like an SFT. Suppose I have the product of two manifolds, and I have a SFT for both factors in the product. So so suppose my manifold is the product of x1, x2. I choose say a separating coisotropic for one and a separating coisotropic for the other, and then I stick in really large max in both directions, and then I see what happens.
So for example, like a curve, like a finite energy curve appearing in this setup could have asymptotics to, like if I looked at its ends, then like the characteristic, I could asymptote to like a characteristic in one kind of codimension 0 piece, which is open and then goes and meets a characteristic from the other piece, for example, like.
Yeah, so you could have sort of matching here at codimension 1 things, but then you could also have matching here, sort of in codimension 2 corners.
Yeah.
And
but for example, could I have a puncture that asymptotes, that doesn't necessarily completely asymptote to any one particular stratum? Do you know what I'm asking?
No, it's always gonna asymptote to some torus orbit in one of the corners.
Cross point or point of cross.
Yeah, right.
Okay.
Yeah, right.
Okay.
Yeah.
Okay.
Yeah. So this would be the sort of the simplest example.
Totally.
What generally do you have these broken structures, broken symplectic structures for instance, if you are given a monotonous symplectic manifold?
Yeah.
It's like the toric degenerations of one varieties. In what generality do you actually have this type of structure? This type of decomposition?
Well, the compactness stuff is completely general. It doesn't require any sort of is that you worrying about the monotonicity?
No, I was asking, like you had this, initially you started with some.
Like when does the P exist?
When does the P exist?
Yeah, I don't have any sort of good.
P or the decomposition, like this.
Yeah, like suppose you have an L. Can you always find a P which sort of isolates it in a toric piece? I don't really.
L, for instance, even if we ignore L, can I always decompose a fellow variety, for instance, into this?
Well, stupidly, to take a completely stupid decomposition, you could always take a Darboux chart, right? And then you could take the circle action coming from the Darboux chart. That would decompose into 2 pieces. So, okay, I mean, there's always at least one decomposition, but that's a pretty useless, well, not completely useless, because it shows you that the Lagrangians and the Darboux charts are weakly unobstructed. So that's how I would say that the Floer cohomology of at least one Lagrangian in any symplectic manifold is.
But the pieces won't be toric in this case.
One of the pieces would be toric and the other one wouldn't.
Yeah.
So, yeah, but you might hope for something like, by taking a sufficiently fine decomposition, maybe you could ask like which symplectic manifolds can be generated into toric pieces glued in interesting ways. I don't have any good answer for that question.
Because in situations where algebraic geometry produces degenerations into toric, not toric variety, but
Yeah, so if you have like in the case of the flag manifold, if you look at the toric degeneration that comes from like Nishinu et al., and then you can see that you can find a good P which is compatible with that. That would be one way, but I don't know any sort of nice sounding results about when P exists or doesn't exist.
also you mentioned somehow breaking L as well, breaking the Lagrangian.
Yeah, so we didn't do the case that L extends across the neck. So that would be another.
Do you have a local, proposal for the local structure for the Lagrangian near the neck, or how does it, or how should it look?
Well, I guess you would just assume it's cylindrical on the neck pieces, and then you in your broken maps you would allow disk components and sphere components in all kinds of parts of the degeneration. It seems like it should be okay, but we didn't check everything.
But I guess you can still take disjoint unions.
Yeah, you can take disjoint unions. Yeah,
Elsewhere.
sure. Yeah.
Any other question? If not, let's next.